Hi, I'm Shireen. In this video, I'll be presenting our work on random set neural networks accepted at ICLR 2025. This work is funded by the European Union's Horizon 2020 project called Epistemic Artificial Intelligence. The core idea behind random set neural networks is to use set valued observations as the basis for uncertainty estimation. And to do this, we use the mathematical framework of random sets. A die is a simple example of a discrete random variable. Its probability space is defined on the sample space where each of its faces 1 to 6 are mapped to the real numbers 1 to 6. Now imagine that faces 1 and 2 of this die are cloaked and we roll the die. Actually, the probability space of the die itself has not changed because the die has not been physically altered. But what has changed is the mapping from the faces to the real numbers. Instead of the one to one mapping between the faces and the real numbers, we now have faces 1 and 2 that are mapped to the set 1, 2. This kind of mapping is a one to many mapping, and this represents a random set. Belief functions assign normalized and non-negative mass values to subsets of the sample space. The figure shown here is an example with mass values for both singleton and non-singleton sets. Belief functions can be computed from these mass values by summing the masses of all the subsets of the focal set. A credal set so formed represents the uncertainty in the prediction. The center of mass of a credal set is called a pygnistic probability. We use both random sets and belief functions to obtain a belief function encoded ground truth, which we then use for training in our random set neural network. Consider the original one-hot encoded ground truth and classification, where classes range from 0 to n. The true class is assigned a value of 1 and 0 elsewhere in the one-hot encoding of the ground truth. We extend this one-hot encoding to a belief function encoded ground truth over sets of classes. The belief function encoding is true everywhere the true class is present. That is, for every non-singleton focal set where the true class is present, including the universal set. Since the complexity of 2 raised to n number of classes is huge, we propose a budgeting technique of sets that can reduce considerably the number of the focal sets that are used in the training of the model. This budgeting uses feature vectors from a feature extractor, fits a Gaussian mixture model over each class of these features, and computes the overlapping clusters over this data as an intersection over a union. And the classes with the largest overlap ends up being the relevant subsets. We have a smaller number of k-relevant subsets now to train the model. In step 2, our model is trained using any backbone architecture, which can be ResNet 50 or a vision transformer. Our model is trained to predict a belief function over sets of values. And this is done by training the model with belief encoded ground truth and minimizing a binary cross entropy loss with some regularization. The predicted belief values are then converted to mass values using the Mobius inversion formula provided in the paper. A probability-like estimate called the pygnistic probability is then computed from these mass values. The pygnistic probability is given over the original classes. We also obtain uncertainty measures in the form of pygnistic entropy and a credal set over all the classes. RSNN has shown to perform really well on datasets ranging from MNIST to ImageNet, while having an inference time the same as a standard neural network with no uncertainty estimation. We also show results on outer distribution detection, where RSNN is able to identify the outer distribution data better, and results on in distribution versus outer distribution entropy. We provide further experiments and detailed ablation studies in the remaining 20 pages of the supplementary material. We also show how RSNNs are robust to adversarial attacks and can also provide statistical guarantees using simple conformity scores. You can read the full paper by scanning the QR code here. Thank you.